This is Chapter 8, Section 4. We are going to look at solubility equilibrium and talk about the solubility product constants and ion products. Again, very wordy on some of these, so I will go kind of fast. You make sure you get down the information that you need. A saturated solution contains the maximum amount of solute possible at a given temperature and equilibrium with an undissolved excess of the substance. It's not necessarily a concentrated solution, even though it might be saturated. The equilibrium principle developed in this chapter will apply to all saturated solutions of sparingly soluble salts. So that is the important part of what we're looking at. If you were to look at your solubility rules, we are looking at things that are considered to be sparingly soluble salts. The heterogeneous equilibrium system in a saturated solution of silver chloride that contains an excess of the solid salt is represented here. There's the reversible reaction that you see. And the solubility product constant of a substance is, and we'll give you an equation that goes with this that you can use. It is the product, that means you multiply the molar concentrations of its ions in a saturated solution. Each of these are raised to the power of the coefficient of that ion in the balanced chemical equation. And again, I said we will go through several examples before this is over. In this one right here, here's the KSP setup, or the solubility equilibrium expression for silver chloride. Because both of these were raised to the first power, you can see that we do not have exponents that are shown because they will be understood as 1. Understood as 1. For a saturated solution of calcium fluoride, this is what our equation looks like. Notice that we have 2 fluoride ions in solution for every 1 calcium ion. And the expression would look like this. Here's that G again. I don't know why it pops up like that, but that is F minus, or again, F minus raised to the second power. But whenever you were to do, if you were to put in numbers for this particular one, the solubility is given here per 100 grams of water, and it is expressed with a concentration of 1.1 times 10 to the negative 3 moles per liter. So moles per liter is going to be what we're using for molarity, or our concentration. And we will come back to this example, how you actually use the numbers that you see represented here and what we're going to do with them. So you write a balanced chemical equation first. Remember, we're only going to look at the solubility product for salts that have low solubility. Make sure the reaction is at equilibrium. The equation should always be written so that the solid salt is the reactant and the ions are the products. Then we'll write our solubility product expression. We have to include concentrations of our ions, but anything in solid or pure liquid form do not take place. And we will remember KSP values depend on temperature. So going back to the example they give, calcium fluoride does dissociate to where you have double the amount of fluoride ions as calcium. So notice when they gave us the concentration of 1.1 times 10 to the negative 3, we have now doubled that for fluoride since we have 2 fluoride ions in concentration, because this breaks down into Ca2 plus and 2F minus. So that has been doubled. We're going to plug those values into this expression. So again, you do see a 2 here that's raised to that exponent because that is the coefficient that we had. Plug it in, you do your math, you get 5.3 times 10 to the negative 9. And this right here is the ion product of our solution that we have. So calculations of KSP, we're going to look at just using 2 significant figures. In this table right here, it's showing you a lot of our sparingly soluble salts and their typical KSP values, these are at 25 degrees Celsius. So if you change the temperature, these values will change. You will need this information on your homework. If you're in class, I'll give you a copy of this. It's off of page 589 in our book. It'll also show you the ion product setup for each of these two. So the solubility product constant is an equilibrium constant representing the product that, again, multiply the molar concentrations of the ions. It has one value for a given temperature. The solubility of a solid is an equilibrium position that represents the amount of solid required to form a saturated solution with a specific amount of solvent. So, it will have an infinite number of possible values depending on the temperature or even the presence of a common ion. So we just talked about common ions earlier in this chapter too. So make sure you get this down and you understand the difference. We're going to go look at some examples. Make sure you write down these examples and then how we solve for each of them. In this one it says calculate the KSP for copper 1 chloride. It gave you the formula. And it gives you the solubility of the compound at 25 degrees Celsius. So here we have it written as 1.08 times 10 to the negative 2 grams. That's going to be our CuCl per 100 grams of water. If we're going to try to put anything into our KSP, it's got to be in moles per liter. So we're trying to get this switched over to where we can deal with solubility in moles per liter. So to do this, we have to do some switching around of some units to try to get to moles per liter. So I'll go ahead and show you what that's going to look like. To get rid of our grams of water, so grams of water here, if I can get over to milliliters of water, I know that based off the density of water, that is a 1-to-1 correlation. Again, based off the density of water, that's density is mass over volume. Now, if I want to get rid of milliliters, I know that 1,000 milliliters is in 1 liter. That is great. I have liters in my denominator now because, again, I am trying to get to moles per liter. So with liters in the denominator, that is good. Now, to get grams of copper chloride to moles, I can put grams of copper chloride right down here. It is based off 1 mole. And I would go to my periodic table. I would find the mass of copper chloride. There's 1 atom of each, and that is 99 grams that you would calculate there. So 1.09 times 10 to the negative 3 moles per liter of the copper 1 chloride. That is going to be our solubility, and that is the concentration of our solubility. Now we can use that information to plug into our KSP expression. So I'm going to leave that right down there, and I'm going to start to work right up here at the top. So now that we have that value, our KSP expression for this one right here, that is copper times the chloride ion that we're setting up here. Those were a 1-to-1. All of our coefficients were 1, 1, and 1. I plug in my values that I have, 1.09 times 10 to the negative 3 times 1.09 times 10 to the negative 3, and I calculate my KSP, and KSP will come out to be 1.19 times 10 to the negative 6. And if you go look at your KSP values from the table we had just looked at, you will see that this value is very close to that value. So here's one of our examples. And again, this information that you see right down here, you're probably going to have to do that several times. Again, That part is based off of the density of water. This is just a straight up SI conversion. In this, it's saying that your solubility product constant can be used to determine the solubility of sparingly soluble salts. The salt we're looking at here is barium carbonate, and you can see it breaks down into the barium and carbonate ions. Notice that their charges are offsetting, so 2 plus and 2 minus. This is what the KSP expression would set up. Again, that should be a negative right there, so CO3 2 minus. And this is also, that's a negative 9 right there. So anytime you see that thing that looks like a G, it's supposed to be a negative. So it's just breaking it down for you here. Since the ions are going to have the same concentration, you could just say x squared here equals this 5.1 times 10 to the negative 9th. So if you had to back calculate the moles of barium carbonate, you would take the square root, find your value of x. Again, that would be a negative 5 on the end of this one. And then the molar solubility of barium carbonate is 7.1 times 10 to the negative 5th moles per liter. So in this one, we are working backwards. We had the KSP value. We're going to find the concentration of our different ions. So another sample problem here. Calculate the solubility of silver bromide in moles per liter and using the KSP value for this compound. So you could go look at the KSP value in the chart for silver bromide. There is the breakdown of silver bromide. All the coefficients are 1, 1, and 1. And if I look at my KSP value, which I will just write it out ourselves, KSP is equal to Ag ion plus the bromide ion equals 5 times 10 to the negative 13th. Because these are 1 to 1, you could place x's in there for each of those. That could be x, that could be x. So we end up with x squared is equal to 5 times 10 to the negative 3. If I want to solve for this, I could take the square root of both sides, solve for x, and you get, that's actually a negative 13, not a negative 3. So negative 13 is the exponent, and you take the square root of it. 7.1 times 10 to the negative 7, and that would be in moles per liter. So that would be the concentration of each of your ions there. Some more information here. Equilibrium condition does not require that the two ion concentrations are equal, so we will look at an example of where they're not equal. If the ion product is less than the value of KSP at a particular temperature, the solution is unsaturated. So we can have our ion product being different from the KSP value. If the ion product is greater than the value for KSP, the solid will precipitate. The solid will precipitate. So, unequal quantities of barium chloride and sodium carbonate are dissolved in water. The solutions are mixed together, so the ion product for the barium carbonate exceeds the KSP of just barium carbonate, which is a precipitate that forms. Precipitation continues until the ion concentrations decrease to the point at which the two ions equal the KSP, and the solubility product can be used to predict whether a precipitate forms when two solutions are mixed. So we have two salts here that we're mixing together, and it's, basically it's a double replacement reaction, and our double replacement reactions occur if a precipitate forms. So now we're looking to see, will this precipitate actually form in this double replacement reaction? So you've had your solubility rules. Now we're throwing numbers with it so that you can see how it all ties in together. In this sample problem, you're going to want to write this down, and then we're going to work through how you get to the final answer. This one is a little different than the previous ones we've done, because now the real question is, I'm not looking at just one salt and the KSP value for the one salt. I'm asking, if I mix two salts together, again, double replacement reaction, will a precipitate actually form? Will a precipitate form? In this example, we're going to take 0.1 molar barium chloride, 20 milliliters of it, an equal volume of 0.005 molar sodium sulfate, and we're going to show you the math to figure out, hey, is this actually going to happen? Now, the math is going to be a little bit on the long side, so make sure you get down each of the steps that we're going to do within this math problem. Here's the information that we have. So you've got your information for your barium chloride and that for your sodium sulfate. If I were to look at this reaction, and again, both of these would be aqueous solutions if you're writing down your phases. And for a double replacement reaction, again, these are ionic compounds. Look at their charges. Barium's a 2+, chloride's a 1-, sodium's a 1+, sulfate is a 2- over here. And your products, barium sulfate, 2+, 2- charge cancel. And then your sodium chloride, 1+, 1- cancel. You can go back and balance this reaction too. There's a 2 right over there. I know from my solubility rules that this is considered to be still in solution because it is soluble in water, your chloride is. But the barium sulfate, this is the one that wants to precipitate out. So we're going to put a solid right there. This is the part of the equation that we're going to focus on. So the KSP value for your barium sulfate, you have your barium ion and your sulfate ion. If I were to go look at its actual KSP value in that table that we had just looked at, it is 1.1 times 10 to the negative 10. So once I get through with my math, I'm going to ultimately find the ion product of the barium and sulfate, and I'm going to compare the ion product to this KSP value that's in the table to see will precipitation occur or not. So I have this right here. Let's go and add us another chalkboard and get busy. First thing, you need to find out the mole quantities of your barium and sulfate ions. So calculate the mole quantities. So we've got 0.020 liters. Remember, it was 20 milliliters, so we're going from liters to moles of the barium ion. The molality or molarity that was given was 0.010 moles of barium. That was the barium chloride. So since the barium ion is coming from barium chloride, I'm using the 0.010 moles per liter there. And that gives me this number of moles of the barium ion. I'll do the same thing with the sulfate. The sulfate, though, was coming from the sodium sulfate, so I'm using that information. That also happened to be 20 milliliters, so that's 0.020 liters. And again, liters per mole, this is for the sulfate ion, so I have to use the information from where it's coming from, and the molarity given was 0.0050 moles per liter. Calculating that, 0.00010 moles of our sulfate ion. So that is our mole quantities. That is the first step. The second step, we are looking for total volume. Total volume. Well, total volume of this right here, we have 0.020 liters plus 0.020 liters. That's the volume of each of the solutions. So 0.040 liters of total solution here. And now we're going to look at the ion concentrations. Ion concentrations of the combined solution. So total solution. Ion concentrations of the total solution. We have 0.00020 moles of the barium ion over 0.040 liters. Using significant figures, though, that should be 5.0. Again, moles per liter. This is for barium. And doing the same thing with the sulfate. Again, same total volume of solution. And you get 2.5 times 10 to the negative 3. So that is our ion concentration for the combined solution. Now we are ready to use this information to calculate our ion product, because we're going to compare our ion product to the KSP value that was in the table. So, calculating the ion product. We had our barium ion and our sulfate ion, and again, those were neither one of these are to a particular power, because it was 1 to 1 and the coefficient in front was also a 1. So plugging in my information there, 5 times 10 to the negative 3 for barium. Sulfate's concentration was 2.5 times 10 to the negative 3. And when we calculate that, we get 1.25 times 10 to the negative 5th. So this is the ion product, Now we're going to compare the ion product to the KSP value. And again, the KSP value was, we looked that up earlier, 1.1 times 10 to the negative 10. And in this case, the ion product is greater than the KSP value. So since the ion product is greater than the solubility product constant, precipitation will occur. So precipitation will occur. Again, lots of steps to get to where we were trying to go with that. I hope you got them all down. There are some limitations to KSP. The solubility product principle can be useful if applied to sparingly soluble salts. It cannot be very useful, though, to solutions of moderately soluble or very soluble substances. That's because your positive and negative ions will attract each other, and that attraction is appreciable when the ions are close together. So sometimes you have to consider two different equilibria at the same time. The equilibrium calculations, again, this is just us kind of breaking it down here. You have a sample equation there at the top. If it's a slightly soluble salt in water, then we can go in this direction here, look at our solubility product constant KSP, and then this is what your ion product would look like, trying to come up with that. Other reversible reactions, those are going to be things that are very soluble. You see, we've already looked at our equilibrium constants, and then the problem looks like this with your products and your reactants.